Okay, so we're going to take a look at a proof by cases. All right, so the idea behind this is that we have some kind of implication, P implies Q, right? And the idea is that we can clearly define the different cases that make up P, right? So P can be broken up into different cases which we logically it means P1 or P2 or P3, etc., or P sub n, right? So there are n cases for in a finite number of cases for our hypothesis statement here if, and then that each one of those implies Q, right? In other words, it's logically equivalent to say if I have P1, then that goes to Q, and P2, that goes to Q, etc., all the way to n, P sub n, that goes to Q, right? So that each one of those cases leads to the conclusion, right? So the idea is if we want to use this correctly, right, we have to make sure that for our if statement that whatever that hypothesis statement is the P statement, that I could very clearly define it into however many cases that I need to. All right, so let's look at an example so we could see how this works in effect here, right? So let's say that if n is an integer, then 2n squared plus n plus 1 is not divisible by 3. Okay. So first, the idea of divisibility, right? So divisibility, we can think of being able to write some integer like this. If it's divisible by 3, then essentially we can think of it like a multiple of 3, right? So if you think of, say, 1, 2, 3, 4, 5, 6, and the other way too, right? Going, the negative integers, 0, negative 1, negative 2, etc., right? We can still think of divisibility in this way, right? Now, the cases I want to take for n, right? So if n is an integer. So I want to focus on, since the resulting statement, the conclusion is that it is not divisible by 3. So what I want to do is I want my cases to be of all the integers, of course, because n needs to be an integer. But I want to focus on those that are divisible by 3 and those that are not, right? Now, here is where the cases part has to be constructed in a proper way, right? So if we think of the numbers that are divisible by 3, right? 3, 6, 9, 0, negative 3, negative 6, etc. Right? So the other integers, how I can describe them is in terms of their remainders, right? So we can think of the number is, you can think of the cases as being the number is divisible by 3, so there's no remainder. The number is not divisible by 3, but it has a remainder of 1, right? Think of 2 and 4, right? And 7 being the next one. All right, and then the other option is it is not divisible by 3, but it has a remainder of 2, right? Think of 1, right? 5, right? Now these three cases, I can represent all of z, okay? Right, which is what I want, right? If n is an integer. So now we have our cases, and each one of those, right, represents all of z. So I have my structure for my proof by cases, right? So let's take case 1, right? So case 1, right, we'll let n equals to 3k. All right, and then I'll look at my, so 3, 2, 3k squared plus 3k plus 1. And here I'll simplify here. So 3k squared becomes 9k squared, and there's a 2 on there, so we get 18k squared plus 3k plus 1. Okay. All right. And now we could see here if I can factor out of 3 out of these. Let's say 3. And then we have 6k squared plus 1. Okay. Now notice I didn't factor out a k here because I want it in this form, right? Remember, the integers are closed under scalar multiplication and multiplication here of another integer. All right, so looking at it this form, right, this is an integer, this is 3 plus 1. So we could see that this is not divisible by 3. Okay, so that proves case 1. So now let's look at case 2. Case 2, we have n equals to 3k plus 1. So we get 2 3k plus 1 squared plus 3 3k plus 1 plus 1. All right, let me simplify here. So we got 2 9k squared plus 6k plus 1 3 3 6 1 plus 3k plus 2. All right, and now distributing that 2, we get 18k squared plus 12k plus 2 plus 3k plus 2. All right, and then combining like terms, we get 18k squared plus 15k plus 4. Okay, and here we can see 18, excuse me, has a factor of 3, 15 has a factor of 3. 4 does not, right? But I can rewrite this as 18k squared plus 15k plus 3 plus 1. Okay, and then looking at this part here, I could see, oh, that is a factor of 3. And we get 6k squared plus 5k plus 1 plus 1. And again, right, the form of an integer that is not divisible by 3, right? Because this whole thing is an integer. That part is divisible by 3, but then we have the plus 1. So we have that quantity is not divisible by 3. All right, so we have proved case 2. Again, not done yet, right? We still have to prove for all integers. So now we need one more case, right? Our third case, case 3, let n equal to 3k plus 2. And we do the same thing, right? So here in this case, we have 3k plus 2 squared, 2 plus 3k plus 2 plus 1. All right, and then distributing here. All right, so 9k squared plus 12k hold on a second here. Okay. All right, excuse me. I thought I made a mistake in the previous one, but I think we're good here. 3k plus 2. Okay. Okay, so 6 and 6 is 12. The last one is 4. All right, plus 3k plus 3. All right, and again, let's start distributing that 2. 18k squared plus 24k plus 12, no, plus 8. plus 3k plus 3. All right, combining like terms, we get 18k squared plus 27k plus 11k. Excuse me, plus 11. Okay. All right. And here, again, we have the first two terms have a factor of 3. The second one doesn't, but if I rewrite it in this way, plus 9 plus 2. Now we can factor the first three terms by factoring out a 3. Right? And again, it's of the form here where this term here, multiple of 3, but then add 2, it is no longer a multiple of 3. In other words, it is not divisible by 3. All right, and that is how we construct a proof by cases.